Well, hello, my name is Mike McLernan. I am with MathWorks Technical Product Marketing, been here for many, many years. Today I would like to talk to you about ISAC. Some people like to say ISAC, but in any event, it is Integrated Sensing and Communications. So I happen to be pretty convinced that this is going to be a critical technology for 6G. And it so happens that multiple players in this wireless game care about it. There are people in the government and aerospace and defense industry that care. There are people in the communications electronic semiconductor industry that care about this as well. So this is a facility whereby one waveform can be used for multiple purposes, for communications and sensing. I'm going to show you a little bit of a demo that incorporates that, uses hardware. This is going to be a USRP radio that we use. But before we start pointing to the radio, I would like to just set up the scenario with you. So if you look at this diagram here on the left, you see an icon of a base station at 0, 0 in Cartesian coordinates. So it's sending out signals. And it's sending out signals to a phone, user equipment, a UE in green, at 0, 60 in the plot. And then there's also a drone. He's going to be winding its way around, all around. And the idea is that the base station signal is going to bounce off the drone, and then it's going to be received by the UE. Now, that UE is also going to receive a signal from directly in the line of sight from the base station as well. So we've got a multipath situation going on. And it turns out that you can, in a bistatic case, that UE is going to be able to tell range and Doppler information on the drone. And so if we look over here, this demo is going to plot range and Doppler in a map. And one thing that is useful to note that there's this little yellow square at 0, 0. That guy is going to show the line of sight path because we don't have any motion with our base station or our UE, and so we don't expect any Doppler. And then finally, we'll have some instrumentation that talks about the signal quality from a communications perspective. So anyway, that's the scenario. Let's talk a little bit more about the hardware setup that we'll be using. So this is a block diagram of the setup, and I'll walk you kind of through the signal flow of what's going on. We've got MATLAB on the left. We've got a USRP N310 radio on the right. So we start in the upper left with an OFDM waveform generator. Now, one thing that's very important to note about this OFDM, and this must be done for all OFDM signals, you have to put pilot signals in that OFDM signal so that a channel estimate can be generated. So again, keep that in mind. We start by generating the waveform, and then we send that signal over Ethernet. So here we have some Ethernet right here into the USRP N310. So it goes into the RF0 port, the TXRX port, and then it is promptly sent out. So that is meant to emulate the base station. So that's the base station transmit signal. Goes over the air a short distance, and then back into the receiver. And then from there, it goes into an FPGA. Now, what we have done here with this FPGA, we are emulating a radar target by imposing Doppler, path loss, and latency on that signal, just like a regular radar target would do. So once those impairments are imposed upon the signal, it gets sent back out from the FPGA back out to another transmit port, where it is then transmitted over the air, received once again. So this RX2 port in RF0 and TXRX port in RF1 essentially acts as a radar target. It emulates the bounce, the reflection off of the drone and then into the receiver. And then finally, that RX2 at the very bottom, that emulates the UE, the user equipment that is going to do the communications processing. However, in this demo, it is actually done in MATLAB. So we go from the radio once more, again, over Ethernet to where we have OFDM receiver and range Doppler processing. From here, we can go to MATLAB. So let's just go ahead and do that. I'm going to show you just a wee little bit of code. So this is an executive. There's several thousand lines of code underneath that, but we just want to run this example. So we're going to create a custom OFDM target, and then run our ISAC simulator. So we click Run. All right, so now we see this guy in action. So the drone is flying all around. Now, in the real world, this would be in 3D space, but in our simplified world, it's just in 2D space. And so what we are seeing is that there is processing going on by the UE to collect channel estimates on a time-varying basis. So what happens, and now I'm going to flip between communication speak and radar speak, is that these channel estimates are being generated by the pilot signals in 5G speak, the DMRS signals, and then they're enabling a channel estimate in the frequency domain. And then what happens, these channel estimates are made over a periodic series of sequences, and then these channel estimates are essentially concatenated in time. So now, if you look at one slice, there's a channel estimate that is across frequency, and that can be used to collect range information. So in radar speak, that would be the fast time. So we can just perform an IFFT on that channel estimate and get an impulse response. When we have that impulse response, the peak of the impulse response will tell us what is the delay. So that gets us our range estimate because it's very, very trivial to convert delay into range. And then with the concatenated channel estimates over time, we are noting that these channel estimates are evolving over time. That tells us what kind of Doppler is happening. Then when we do a forward FFT across these evolving channel estimates, then we can get an estimate on the Doppler. And so it's actually very, very straightforward. And so, in fact, I'm going to show you ever so briefly the code used to do this. You can see there's nearly 600 lines of code in this OFDM processor. It turns out that all the channel estimation has to be done anyway for OFDM demodulation. All of the single carrier demodulation, the OFDM, channel equalization. It turns out that there's essentially 3 lines of code that do the lion's share of the work of the radar processing, lines 562 to 564. You've got an IFFT to convert channel estimates back to the time domain. That's the fast time. And then the FFT of the range Doppler grid does an FFT across the slow domain, and then the FFT shift is just to get it so that our eyes are used to seeing a response. So really, 3 lines of code. There's some housekeeping going on as well, but the lion's share is just these 3 lines. So what this means is that in any OFDM-based communication system, it is almost trivial to add radar processing to it. Let me go back to the diagram here. And so let's talk a little bit about this range Doppler plot we see in the center. So it took me a little while, about 2 minutes of staring at this the very first time I encountered it, to convince myself that the motion that I see on the left corresponds to the range Doppler that I see on the right. And this is because this is a bistatic case. The UE is calculating the range in the Doppler as it sees the reflection off of the drone. You'll notice that from a radar and sensing perspective, the UE knows nothing of the base station. It's calculating these numbers purely from the reflection from the drone back to the UE. And so here again, the brightest yellow spot is in that 0, 0 range in Doppler. So that is indicative of the line of sight path. So then if we focus a little bit more on the graphics on the right, so what we see at the top right is a received QPSK symbol. I've neglected to mention that we've got single carrier QPSK modulating every subcarrier of the OFDM signal. And we're going to note that when the drone passes directly in between the UE and the base station, you'll see the constellation. Yep, it gets to be more what you would expect for QPSK. Because you'll notice that it is phase equalized. You know, we see the x's there, but the amplitude is kind of messed up because of the multipath. But when the multipath is gone, because the drone is in between the base station and the UE, then there's only a single path. and then we see the QPSK constellation as we would expect. And then that final gauge on the right is just basically a 1 minus BER meter to indicate, yes, indeed, the communications waveform is being demodulated correctly. And we see it's pegging out at 100%, so it's perfect communication. Let me focus our attention just for a moment on the radio. So I've walked you through the block diagram, but I'm just going to tell you what's going on with the USRP. We start transmitting on this antenna over the air and to this antenna. This second antenna is simply emulating the target. And so then that signal gets sent into the radio. The FPGA inside the radio has a bit stream imposed upon it that models and emulates Doppler, path loss, latency. And then that impaired signal comes back out, is transmitted over this antenna. Again, it emulates a radar bounce. This is the reflected path, if you will. And then finally, this fourth antenna is just the UE receiving the signal that has both a line of sight component and a one reflection component. And that's how the radio gets to play ball with this example. So I hope this has been helpful to you, and I look forward to talking with you again. Thank you so much.